Thanks for having me here. And today I'll be talking about the title is on the journey of redefining stream processing. What do we learn from building Risingwave? And I'm Yingjun Wu, and from Risingwave Labs. I was actually from, I'm based in San Francisco area, but it's pretty nice to have the chance to speak in Berlin. It's actually my first time to meet up in Berlin. Yeah, I can speak at a meetup in Berlin. So now I'm a founder of Risingwave Labs, and the previous to starting the company, I was at Redshift. And before that, well, I was at IBM Research in London. And I obtained my PhD in the area of stream processing and database systems. So one slide about the Risingwave. To be honest, every time I talk about the Risingwave, I mean, especially, to be honest, in Berlin, when I talk about Risingwave, it's like okay, using Google Meets in Microsoft, right? It sounds like kind of strange because well, you know that okay, Berlin was the place where the famous Apache Flink project was invented, right? So, but anyways, yeah. So what is Risingwave? Just one slide. That is what is a distributed streaming SQL database, and we open source the streaming SQL database under Apache for the old license. And within just 1.5 years, and we have already gathered 5,000 GitHub stars, and we have a lot of contributors and thousands of faculty members. And the system have already deployed over 100K using Kubernetes. So where we can use streaming database? I mean, people may think about okay, fintech definitely for sure, right? Gaming and probably some let's say places for gaming and some definitely stocks, right? But the interesting thing here is that we actually have our customers from different industries like aerospace, like food chain, right? And manufacturing. We actually support a company. We actually have a customer who is producing 1/3 of the world's TV motherboard. And also energy. We also one of the customers is the European's largest energy company. So yeah, that's what we really found for, and we found that okay, this domain is actually pretty interesting. So as I just mentioned, well, we started building the company 3 years ago, and I didn't really expect that. Okay, when we discussed about the meetup, holding the meetup with Ivan, we didn't really expect that the talk will be only 30 minutes. So essentially, I have to summarize my 3-year journey within 30 minutes, right? Okay, let's start. So first of all, let's go back to 2020. And in 2020, I was doing Redshift. So Redshift, I because everyone should know what Redshift is, right? Redshift is a data warehouse, right? If you use AWS, then probably you will use Redshift because well, that's the default data warehouse you can get, right? In Redshift, if you use Redshift, most of the people use it for batch, right? I mean, we can have, let's say, data can be stored in S3, right? So you can have the CSV stored in S3 and bulk loading to AWS Redshift, right? And then you can generate a dashboard, right? What people usually do is that they probably run an orchestration tool like Airflow, like whatever, right? And then probably run some people actually run it manually every 6 hours, right? And every 6 hours they trigger the computation and then generate a report. That's what they do. But gradually we find that okay, Redshift actually more and more people are using connecting data, dumping data from Kafka to Redshift, and probably from PostgreSQL to Redshift. Actually in AWS it's RDS and Aurora, so can be Postgres, can be MySQL. But we do see that actually people are moving data from Kafka, Postgres, and some other places to Redshift. And this kind of data is kind of streaming data. Probably you can say that Postgres is not streaming, but people just some people just use, let's say, directly just the data from Kinesis, right, or Kafka, right. So such kind of data is definitely streaming data. So if we continue using Airflow, then what do we have? Let's say that okay, we want to orchestrate we want to run the view, right? So we create a view and run the computation every 6 hours. Yeah, it'll be great, right? We still can generate a report every 6 hours. But remember that what you can consume from the Kafka or from Kinesis is the streaming data. If you consume streaming data, right, in a streaming fashion, they probably don't really want to just have really generate report in 6 hours, right? You probably really want to generate report every, let's say, few minutes, right? I didn't really follow Airflow closely, but I'm not sure whether it can orchestrate this, trigger the computation in second level, but for sure it can trigger the computation in minutes, in 1 minute, right? But the problem here that if you use Airflow to trigger or some other orchestration tools to trigger the computation every single minute, you will find that Redshift doesn't really work. Right? Why it doesn't really work? The reason here that's Redshift is a batch system, and every time you trigger the computation, essentially Redshift needs to scan the entire table from the Redshift doesn't really support index. I'm not sure whether you know that, but so Redshift needs to scan the entire table and find this, but it does really have the errors in tree, similar structure. It will scan the entire table and fetch the data, which can be super slow. If you trigger the computation every single minute, then probably the query will run for probably several minutes. Then you'll find that you will never generate a report. So that's the problem. So what do we need? And that's why I come on and try to build a startup. And what I think is that we actually need a system that is definitely optimized for stream processing, because we have streaming data. It's kind of natural to use stream processing instead of batch processing, right? Otherwise, we can just use Redshift, right? And the system should be easy to use, right? It should be simple, because like people use Redshift, if people use Redshift, they probably don't really want to know too much about the system details about how Redshift work, right? You probably don't really know, whether Redshift supports index, whether Redshift supports secondary index, right? So don't make things complicated. We want to have a system that is simple to use, right? And we also want to make sure that the system is cost efficient, which means that definitely it should be support high performance execution for sure, right? But for the interesting part here that in streaming world is that the workload can fluctuate. It's quite different from batch in that in batching systems you can trigger the queries and then just run it once. If it's slow, then it's slow, right? But in streaming, it's continuous query processing. So and the workload can fluctuate. So you have to guarantee that the system can dynamically scale, right? It can be elastic. And also most important thing here that the system should be fault tolerant, right? Otherwise, if the system crashes, you have to rebuild the system, redo the computation from scratch, which can take days, right? The system won't work at all, right? So we want to have such kind of system. Then what we can do? So let's choose our fighter, right? One is I selected 3 fighters. One is AWS Redshift, Postgres, and one is Betahaus, and one is Flink. And these 3, well, I choose these 3 because I'm kind of familiar with these 3 systems. They're pretty solid systems, definitely, right? For sure, Redshift has tens of thousands of users. In ClickHouse, you know that ClickHouse has a huge community, and Flink, same thing, right? Well, Flink has also gained popularity in a lot of tech companies, right? So let's think about whether we can use these 3 systems to do stream processing, right? Let's first talk about the Redshift materials view. As I just mentioned, in Redshift we can create views, right? And then trigger the computation every not every 6 hours, but every minute, right? And it doesn't really work because it triggers recomputation. Then people will say, look, well, we can use materials view, right? In Redshift we have a materials view, right? Redshift can do can also even have the so-called auto materials view. But unfortunately, Redshift materials view isn't streaming at all. The reason, well, you probably don't really want to argue with me because I was one of the people that work on Redshift materials view. So basically, what Redshift does, what materials view does, is that every time if you want to refresh the materials view, it will rescan the entire table and check the delta set, which means that the table where the update happens, right? What's the the newly generated data and the data that has been updated, right? So it will identify the so-called delta set, and then apply the computation. So it's still kind of batch mode. And auto refresh will only work when the system, it detects that the system doesn't really have a high workload. So it will have enough CPU cycle to do the to refresh the material view. That's how Redshift material view work. So yeah, based on my description, you will know that the Redshift material view won't work for streaming data for sure. Then let's talk about the ClickHouse. Right? ClickHouse is definitely one of the most popular systems used in the if one of people use to use the to support interactive analytics. Right? ClickHouse, did I say Postgres? No. Anyways, ClickHouse is definitely pretty fast. But the problem, and ClickHouse also supports materialized views. But the challenge here that the materialized view in ClickHouse isn't powerful enough. The reason here that think about it has synchronized, so-called synchronized material view, but it only supports aggregation. I think it now supports aggregation. You can check the definition later. But definitely it doesn't really support joins, updates, deletes, and it doesn't really support any streaming functionalities like streaming semantics like time window join, time windowing, right? Or watermarking and some others, right? And most importantly, actually, it's not fault tolerant. Because for ClickHouse, it doesn't really make sense to make this fault tolerant. Fault tolerant means that you have to do checkpointing, frequency checkpointing, and recover from the checkpoint. ClickHouse doesn't really need that because if ClickHouse crashes, then it can just review the system. It can just reboot the system because the main functionality of ClickHouse is to support interactive analytics, which is essentially batch processing. So ClickHouse probably doesn't really work. Then let's talk about Flink. Flink is definitely a pretty great system, right? So most the biggest advantage of Flink is that it's definitely a fully fledged stream processing system, right? It has all kinds of stream processing functionalities like the time windowing, and it also has has a lower level Java APIs, right? Python APIs, right? But as I just mentioned, I come from Redshift. And if you ask me to use Flink, then I'll ask a user to a Redshift user to use Flink. Well, it's different world. It's a system from different world, right? Because for Redshift, it's actually a Postgres system, right? It was actually Redshift was built on top of Postgres 8.0, and it was it provides the users with Postgres experience. If we tell people forget about Postgres experience and let's use some big data system, then people don't like it. So yeah, we can talk more about Flink later, right? But so now we find that fighters doesn't really work. So I have to think about create our own fighter, right? What kind of system we want to create? As I just mentioned, we definitely want to have we create a Risingwave, right? So as we just mentioned, we definitely want to make sure that the system is simple to use because people don't really want to spend a lot of time in learning a new system, right? If I use Postgres, then just give me the Postgres experience. Don't tell me that I need to learn MySQL, right? Well, I just love Postgres, right? And the second thing here that for cost efficiency, as I just mentioned, is small loss. High performance, elasticity, and instant failure recovery, right? So regarding a simple to use or ease of use, all design is that it should be just Postgres SQL style. Provide users with just Postgres SQL style experience. And regarding the cost efficiency, it means that S3 is a primary storage. I will discuss these two things in detail. So let's talk about Postgres experience first. So what it means? It means that we need to be fully compatible with Postgres one protocol, which means that we need to build a system that can talk to any system that is compatible with Postgres. think about one simple example is DBT, right? DBT is probably one of the most probably the most popular data monitoring system in the world, right? And people just want to use DBT to do data modeling, right? And Debezium, the data management system, right, or data management tooling, right? And people just want to use the data management tooling to manage my database, right? And definitely we also need to support Iceberg and Superset, and which is BI tool, right? And BI tool, right? And interestingly, if you support Postgres, well, if you are compatible with Postgres, it also means that people can directly use Visual Studio's Postgres plugin to code, right? To write a SQL code. So we do support for. That's why that's essentially a key reason why we want to make sure that Risingwave is fully compatible with Postgres web protocol. So now we have already implemented that, and Risingwave can support all these kind of systems. Right? But that's just about a SQL, right? People may say that, okay, look, well, I mean, just a SQL, right? Well, I can just, even if I move to MySQL, right? MySQL again also support has it's also easy to use, right? And probably I can also use some other SQL, right? Well, like Flink SQL, Spark SQL, whatever SQL it is, right? Well, we have all kinds of SQL, right? So essentially, PostgreSQL is not isn't convincing enough to tell people that, well, look, the system is good enough, right? Well, the system is simple enough, right? So I think the most powerful thing here that we actually represent the stream processing capability using materialized view. So if we think about it, well, if we use, well, no matter whether it's Flink SQL or probably some other, Flink or probably Spark or whatever stream processing system it is, right? We probably need to create a job, right? But the creating job is kind of tedious, to be honest, well, because we have to write a Java code and then submit the code into Flink or probably Spark, right? And then the system, the framework will do the computation for us, right? But if we have the database experience or PostgreSQL-like experience, then things become simple. The only thing we need to do is that we can just create a materialized view. Then all materialized view should be synchronous materialized view, also called consistent materialized view, which means that every time a new tuple comes in, and if the tuple is covered by is covered by the materialized view, it will trigger the refresh of the materialized view, and then refresh the results stored in the materialized view. Right. That's one thing. But well, that's still not powerful enough, right? Because well, I mean, it's still people will argue that okay, look, we also have, let's say, in Spark we have Spark SQL, right? But and in Flink we also have Flink SQL, right? People can also say, okay, look, I can write a similar SQL code. But the more interesting thing in Postgres or in a database context is that can create materialized view on top of the materialized view. That is, instead of connecting two Flink jobs or two Spark jobs, you can just create a materialized view on top of another materialized view, and without using any connecting system or messaging system, or without using some, let's say, S3 or some other systems. Right? So this makes things much easier to build. I can give you one example. So if a system, if people write Java code or probably write Flink SQL, what they will typically do is like they will write, let's say, 200 lines of code, right? And it's really challenging for people to debug, right? That's where you have so many lines of code. And that's where everyone writes code, right? And then you probably know that for software engineering, it's always recommended to reduce your the code size, right? So probably just want to have 100 lines of code inside of a code snippet, right? So if we have materialized view on top of materialized view, if we have such kind of functionality, it actually means that we can actually chop up the on long term, let's say 1,000 lines code into, let's say 10 smaller materialized views, and it can make things much easier to debug, right? That can totally change your experience. And another thing here that you can actually also validate your results easily. Why? Because for in database systems, everyone should know that the materialized view is parallel, which means that people can directly check the result in materialized view, right? People do not need to, dump the data into some other systems. They can just check the result in materialized view. So in that case, it's much easier for you to debug your streaming job or streaming processing logic, right? It will completely change your experience. So that's about the Postgres style experiments. Then let's talk about the other thing, which is cost efficiency. So the one thing, so as you just mentioned, in terms of cost efficiency, we always mention that in Risingwave design that it adopts so-called S3 as a primary storage design. So I actually feel that it's kind of buzzword because we can also call it like decoupled compute and storage, or probably short storage architecture, or all-tier storage, right? So instead of mentioning all these kind of buzzwords or probably fancy architectures, we can just call it simply style architecture, right? So what it means? It means that instead of basically storing in the stream processing system, we have the state, right? Instead of splitting the state into different machines, right? We can actually put a state in a remote machine in S3, right? And then we can ask those for we can ask the computation node, which is EC2, to directly fetch data from S3, right? So definitely we are not quite stupid because S3 is kind of slow, right? So essentially what we will do is that we will have the local cache in S3, in a local machine. So look at the design. Look at the Risingwave design. If we adopt such kind of design, then it will totally change how the system can recover from failure. Right? If we have let's say a MapReduce like architecture, then if failure occurs, then people need to reboot another machine and load the state into the newly created machine, and then recover, right? So you actually will have some downtime. What's a downtime? Well, if the machine failed, and if you have to load the state into your newly created machine, then you cannot use the machine. You cannot use the service, right? And the downtime is totally relational to the state size. Because let's say the state size is big enough. Let's say 1 terabyte. This morning, someone just told me that one of our clients, they told me that they actually have a state of 4 terabytes, right? Well, if you have some kind of big state, then if the system crashes, you have to think about, you have to reload the state. It can take a pretty long time. If you want to reload a 4 terabyte data, probably it will take an hour, right? Which means that your system will not recover within an hour. But in Risingwave, the design is totally different. Well, if the system crashes, then Risingwave does not need to reload the state into the local machine. What it will do is that it can just the only thing it needs to do is that it can boot another machine, create another machine, and that machine can directly read the state from S3. That's it. There's no downtime. But definitely there are some tricks, right? So the trick here that because we're loading from S3 is still kind of slow, right? So for the first few probably seconds, or for the first few minutes, probably the latency can be pretty high because of the S3 latency. Yeah, but the good thing here that I guess nowadays, you guys all know that AWS has a reinvent, right? They just announced a new S3, right? So the low latency S3, which means that S3 can deliver a single digit millisecond latency, right? So it will totally change the landscape of all the data systems. So that's the failure recovery part. then let's talk about the elasticity. So in terms of elasticity, it's still the same thing. If you use MapReduce like architecture, then if you want to scale from one machine to 3 machines, then it means that you actually need to split the state, migrate the state into 3 other machines, and then wait for and only until the state has been reloaded in these machines, you can scale the machine, right? Well, you can say that okay, the scaling is completed, right? But in Risingwave, it's totally different because, well, as I just mentioned, well, I mean, in local machine, what we have is a cache. If you want to scale from 1 machine to 3 machines, then the only thing you need to do is that we can just create 3 machines and ask these 3 machines to read the state from the S3. It will totally change the design. So yeah, that's about that's about the cost efficiency. So because we don't really have enough time, so we can talk something some interesting topic. That is one is Risingwave versus ClickHouse. I have to say that for Risingwave loves ClickHouse. We actually have pretty good relationship with ClickHouse company. I know that everyone also has a ClickHouse service, right? And actually, we also love Ivan, definitely for sure. Yeah, Risingwave loves ClickHouse because they are optimized for different purposes, right? Risingwave is actually optimized for monitoring and alerting use cases, while ClickHouse is actually also probably Druid or Peanut, right? These kind of systems are actually optimized for interactive analytics, right? So if you don't know, okay, why can we have one system to achieve all of them, or to achieve both the best of both worlds, right? Then think about this. So there's a paper called NAPA from Google, right? In the NAPA paper, the Google guys will introduce a concept called the impossible triangle, which means that okay, in any database system, you can only achieve two out of these three properties. Freshness, which means that okay, the result freshness. Query latency means the ad hoc. If you run ad hoc query, how fast you can get a result, right? And the cost. Cost means a resource cost. For any database system, you can read the paper. For any database system, you can only achieve two out of three. So for Risingwave, it's actually optimized for. If we assume that the cost is consistent, right? For Risingwave, it's actually optimized for freshness, while ClickHouse is actually optimized for query latency. So, right, well, which means that ClickHouse actually can achieve low latency when answering ad hoc queries, while Risingwave can achieve high freshness role if we want to answer continuously answering the predefined queries. So that's a different. So definitely there are some systems that is optimized for cost, which is Snowflake and Redshift are both optimized for cost. Right? And actually, there are also some systems that is actually optimized for freshness and query latency, and they don't really care about cost. That's actually one system. Should not be recorded, okay? Which is single store. Actually, single store is actually optimized. They try to optimize for freshness and query latency, and the sacrifice of cost. So if you want to use Redshift, Risingwave and ClickHouse together, definitely you can. And then one typical case is the web architecture, right? People can ingest the data into Redshift. Sorry, I always say Redshift. Okay. I've already left the Redshift for 3 years, but I love it so much, right? Anyways, yeah, you can ingest the data into Risingwave and ClickHouse at the same time, right? Right, and then use your BI tools to query both databases. And the other architecture is a Kappa architecture, which means that you can use Risingwave to process particular queries, and then deliver result into send the result into OLAP databases, and ask the OLAP databases to answer ad hoc queries. Right. Yeah, because so I know that people love ClickHouse, and a lot of people also love Flink, right? So definitely people will ask me about how you compare with Risingwave and Flink. So the question is that do we really compete against Flink, or we love Flink? So I have to say that the answer is that we can decide. Why I say this? Look, I can show you just one figure, and you can understand why this occurs, right? So in the data world, there are data engine, and then there is database. And in the dashboard, we have Spark, and we also have Snowflake. Do you think that Spark is competing against the Snowflake? Well, the answer is, well, you can decide, right? And same thing, well, in the streaming world, we have Flink and Risingwave. And they optimize for different things, but well, do you think that the Flink is competing against the Risingwave? I mean, you can decide. So, okay, so if you ask me about, okay, don't try to ignore, skip the question, right? Well, try to directly answer this question. So look, so I think it totally depends on use case. What I found is that in most of the companies, well, if the company is big enough, they will actually have two different teams. One is the data platform team or big data team. It totally depends on the company, right? And the other one is called the database team. So database team will only use database, and the data platform team will only use data engine like Spark, right? And similarly, in AWS, we also have database team and the database org, which includes the AWS Aurora, which includes the AWS RDS, which includes AWS Redshift. And we also have the data engine, what is called for the EMR, Elastic MapReduce team, which manages all these kind of like Spark, Flink, any other data systems. So yeah, that's a thing, right? So totally depends on who you sell to. So in terms of compare, if you want to further compare with Risingwave and Flink, then you will find that they actually share a lot of properties. They both support exactly one semantics, right? And they both support watermarks. They both support time wandering functions, right? And they both support database CDC, right? But they support all kinds of stream processing semantics. But what's a different part? So one is that Risingwave is the database, so the experience is like, okay, you create materials view on top of another materials view to express your complex streaming workload, right? Stream processing logic, right? And definitely you can also do query serving, which means that people can directly query the database. Query the materials view, right? To fetch the result. And third thing here that the Risingwave is compatible with Postgres, which means that we can leverage all the data systems in the Postgres ecosystem. But for Flink, well, the unique thing here that it actually it provides lower level APIs like Java API, Scala API, right? But it can also have a Python API, which means that if you have a lot of Java code, if you develop your applications in Java, probably you will choose Flink. Or probably if you're a data scientist, right? So, and if you use like, to be honest, I don't know how much PySpark is, right? Actually, some people compare PySpark to me, but anyways, if you're a machine learning expert, but probably you can use the PySpark, right? So then we further talk about what I only have probably very few slides left, so I can wrap up in 5 minutes. Then let's talk about one thing that can only be done in Risingwave, but cannot be done in Flink. So the Risingwave way for stream processing is that it focuses on simplified stream processing experiments. Which means that if you use Flink, then probably, or if you use Spark streaming, then or any other data system, I know that Google guys will. I mean, if you are in GCP, we know that a lot of guys use GCP speed, which, I mean, yeah, ask for the experience. But yeah, if you use such kind of systems, then typically what you will do is that you have a stream processors, and you will use Kafka to connect to the different streaming jobs, and then connect using Kafka to connect to the database. Right, that's typically what we do if we use Flink or probably use Spark streaming. But for Risingwave actually tries to provide a simplified stream processing experience. What do you say that forget about all this kind of architecture, just use one single database, and you can use materials views on top of the materials view, and you can open up, you can directly query the materials view to see your result. You don't need to have some kind of data set. That's what we say. But for Flink, Flink's key, I believe that's where its unique value prop compared to Risingwave is that it actually has very extensive stream processing capabilities, which means that it actually not only have SQL, right? Well, it also have data table API, data stream API, data set API. Also, if you are expert, Java expert, or probably stream processing expert, you can also leverage subsystem for stream processing, right? To access this lower level thing, right? So, and it also helps you to connect to your Python ecosystem as well as the Java ecosystem, which means that it actually provides you with extensive stream processing capability. Right? Okay, then I only have 3 slides left, and that's the things what we learned within the last 3 years. Okay, so one is that the reliability of how to build a system. So we found that reliability is the most important thing. If you don't, if a system is not reliable, then nobody will use it. Well, all probably people will use it, then people will say, okay, no, your system is not reliable, right? Or your system is not protection ready, right? So if you want to build a new system, definitely you always want to prioritize reliability. And second thing here, you probably want to prioritize is a feature set. Because so, I mean, if you don't really support some key features like for example the in streaming watermark, people don't use it. Well, because people really need that. Well, in Postgres, well, actually we have a lot of people ask for JSON. That's why we actually have pretty strong JSON support, and also UDF. People like it. So feature set is pretty important. And then you can think about the performance. The performance, well, I mean, for performance, what do we think here that for performance, if your audience or if your target users big companies, then probably one of the first things they will ask for is your performance report. Right. So performance, I mean, is still kind of important. The least important thing is all kind of random AI stuff. So yeah, never build such a thing. And actually, some people will ask about, well, okay, do we support LLM? Really? I mean, some people just ask, okay, whether support LLM? No, we don't do that. Yeah, so we just do stream processing. That's it. And the second thing we found is that we always find your target audience, right? So if you want to say that Risingwave is great, and if you talk to database team, they will be pretty super happy because they just want to use a system that can support stream processing, right? So database guys will be pretty happy. But for, I mean, if you say the same thing to big data guys, no, they just hate you, right? So they just say that, okay, no, we probably just want to use a data framework. And the third thing here that we learned is that from batch to streaming, right? So people talk about okay, moving from batch to streaming. How we do that, right? Yeah, that's actually the key question all the streaming vendors need to address. The thing here that what we find is that with these days, well, I mean, a lot of companies, big companies, well, they all talk about streaming, but they didn't really say that okay, we need to use Flink or we use Risingwave. They talk about can we support stream processing in Databricks? Can we support stream processing in Snowflake? Right? So that's actually the key thing we think about, right? So what's the next step for what the market will look like for all the streaming vendors, right? So because all these big vendors like Databricks and Snowflake, and they actually just yesterday we also saw that I mean the day before yesterday, right? So Redshift also claimed that this supports the incremental refresh. I don't believe it because these are all my colleagues, ex-colleagues, and it's just a preview. Preview means that actually Redshift review means that it will be delivered in 2 years. So yeah. Anyways, that's all my talk. Yeah, thanks.
Wave until how it's built, I would say. And I mean, I'm going to talk a little bit about just a different system in terms of I'm going to talk more about Apache Flink, Debezium for change data capture, but then also it's more focused on the use case side of things. So why would you want to use it? What can you actually do in your day-to-day job with the stuff I'm going to talk about? And the problem, the use case I would like to explore a little bit is how you could take data from your operational Postgres database. It's just an example, it could be MySQL, Oracle, SQL Server, whatever. But how can you take your data from your operational relational database over into a search index in OpenSearch? Fun fact, in the past I've done this talk with Elasticsearch, but here we are at open source meetup, so I was mandated to change it into OpenSearch, spend the day to update my demo, it worked, so yeah. And so we want to do this. Why do we want to do this? Well, we would like to do full text search, for instance, which is something which we typically cannot do as well in a relational database. We show, there's some support, but if it comes to proximity search, like fuzzy search, maybe show you like all the proximity of your query results, this kind of stuff. You don't really have this in a relational database. So that's why we like to use a bespoke system like OpenSearch. And then also, of course, we could use this then to try for like dashboarding use cases, LODs, all this kind of stuff. And I would like to explain a little bit how we could build this kind of data. And I should say, I would like to do this in real time, right? Because as the points you made, we don't want to do this in batches like every 6 hours or so, because then our data in the search index would be outdated, search results would be off. We want to do this like in real time, not in the CS sense of the word, but like with no latency, single-digit seconds, maybe 2 seconds, something like that. The tools I'm going to talk about are Debezium, which is an open source tool for change data capture. Has anybody heard about Debezium before? Okay, like here. One third maybe. Who's using it in production? There's always the brave guy using it in production. Awesome. Good for you.
Yeah, we definitely use that.
Yeah, it's also used in Risingwave, right? I want to talk about Flink for stream processing, and I want to show how to use those things in the demo. A few words about myself. I work as a software engineer at a company called Decodable, and essentially what we do is we build a fully managed stream processing platform based on those tools like Debezium, Flink, quite a few others. I work as a software engineer. I used to be the project lead for Debezium in my tenure at Red Hat, and I've done quite a few other things besides that. All right, so let's get started. Coming back to our problem. Well, as I mentioned, we would like to do this in real time. So a batch is off the table, and now the question is, how can we actually get our data into our search index? And one apparent solution may be, well, my application, I could have it write to the database, update its customers, purchase orders, recipes, whatever your business is about. You could write to the database, and then at the same time, you could also send a request to the OpenSearch index for updating the search there. But there's some problems there, and one of them is, well, there is just no way to really make sure that those two things are guaranteed to happen with transactional semantics, because, well, there's just no way you would have like one transaction around it, which means you could end up with inconsistencies. It could happen your database transaction commits, then your application crashes before it gets to issue this request to OpenSearch. Or then if you make that the other way around, I first send the request to OpenSearch. I first send the request there, but maybe then the application crashes. You actually haven't committed in the database. So you would end up with inconsistencies. There's questions around ordering. So how would you actually make sure that if you do multiple changes on the same customer, like in close, time proximity, how to make sure that this ordering is guaranteed across those systems? Very challenging to get right. And lastly, there's an availability concern. So even if you were to solve all those problems, I would say it's not ideal because, well, you need to have those two resources. But what do you do if you just cannot reach your OpenSearch cluster? Maybe it's undergoing maintenance, you have network split, whatever. So, your availability of the system just by definition is lower in comparison to just depending on the database. So that's another reason. So if we cannot do this, well, what else can we do? And this is, where Debezium, or I should say change data capture, can help you with. So the idea there as well, we can, what's going on? Okay, not good about this. Stay with me. So the idea is, okay, we only update data in our database, and then, well, this is the canonical source of the changes of the transactions which our application did, right? Any transactions which come into the system, they will be reflected in events which are added to the transaction log, the while in Postgres, the white headlog there, MySQL to bin log, Oracle to redo log, and so on. So all the data changes are serialized essentially in the transaction log. So this gives us the order. And now if we have a way for getting events out of this transaction log, all the inserts, update, deletes, if we could extract those and then publish them to any kinds of downstream consumers like our search index, well, this is exactly the tool which we need, right? And in a sense, you could say this tool, Debezium or any other change data capture tool, it essentially acts like a replication client, right? So it takes whatever is written to a transaction log and publishes elsewhere. But instead of another database, which by the way we also could do, this gives you connectivity with all kinds of downstream systems, search indexes, caches, data warehouses, real-time analytics stores, whatever you want to do. So, you know, this is what Debezium does, log-based change data capture. So it extracts change events out of your database transaction and publishes them. Now I could do a talk solely about Debezium, what it does. There's like UI support, things like outbox parent support, all this kind of stuff. But really, the takeaway should be it's an open source platform for change data capture. It's very capable. It has a very, very active community with hundreds of people who have contributed. It has massive installations where people use it to stream changes out of hundreds of MySQL databases, thousands even. So it's very battle proven, and even Risingwave is using it. So there must be something. Now, just touching a little bit more on why I think this is a powerful tool. And by the way, I've been working on this for like 5 years, a bit more 5 years. And still I come across new use cases, right? But just to give you like the important ones, well, you would obviously use it for replicating data from your operational database into a data warehouse, into a search index, maybe updating a cache. Then this notion of streaming queries, like incrementally recomputing queries as the underlying data changes. This is something which those change events would enable you to do, right? You would use this with an engine like Flink to do this, but the CDC event stream which would enable it. Building audit logs. I mean, if you have this change log event stream, you put this into Snowflake, add all the events there, it's a perfect audit log, right? And then you can think about how to enrich this with some more metadata to tell you about the author of a change and so on. So tons of use cases, and now I'm big into QR codes lately because I discovered you can in Chrome, you can just download a QR code for any websites. I'm super excited about this. So if you go to that one, you can actually find a blog post which I just wrote, which essentially is this tweet in a longer form, telling you about use cases for CDC and giving you some examples, references to talks I did, and so on. Has anybody taken the QR code? Let me know how it works. Cool. By the way, I have to say, whenever I put a QR code on a slide, I always wonder, is this like a real one, or do I send it to some weird page, right? So it's always like, how can I validate it's the right one? It's kind of cringe. Anyways, so the two things I want to touch on about today is like, this one is wrong. It should be feeding search data. So imagine you red square the first one or the next one. And then also maintaining denormalized views. I will get back to this later. So that's the two things I would like to do. All right. Then, well, what's more, I mentioned, okay, so we take data out of the database's transaction log. And now, unfortunately, there is not a single way for implementing CDC for all kinds of databases. Of course, there's no standardized format for those transaction logs, no standardized API. They all look different across the different databases, which means the Debezium team had to do all this research to create connectors for all those databases. But then the events, as they are published, they look pretty uniformly across all the databases. So for your users, or for you as a consumer, maybe you build a Flink job, it doesn't matter if this event doesn't come from Postgres, Oracle, and so on. Then there's like connectors which are supported by the Debezium core team itself. There's this notion of community-led connectors, where, for instance, in case of Google Cloud Spanner, actually folks from Google maintain their own Debezium-based connector for this database as part of the Debezium project. And also there's even externally maintained connectors. So for instance, Yugabyte or ScyllaDB, they maintain also CDC connectors based on the Debezium framework, which also means that they also expose the same kind of change event format to you. So how do those events look like? And in a nutshell, well, it describes a row in a database which has changed, right? Now, in case of an update, you would have the before and the after state, like old and new state of this row, which was updated. And then within those blocks, well, the structure resembles your table structure, right? So for each column, there would be a field in this change event. And obviously, if it's an insert event, you just have this after part. If it's a delete event, you would just have this before part. So that's before and after. And then, of course, there is also some metadata in addition to this, right? So it tells you about what kind of connector is this, which database, the offset in the transaction log, timestamp, You know, in case of MySQL, we could tell you which kind of query was causing this change. So all sorts of interesting metadata. The transactions, so you could later on correlate multiple events from the same transaction. So all kinds of useful stuff. Cool. Another thing I want to mention on Debezium is, as I mentioned already, it's becoming a de facto standard. So not only the Debezium project itself is, you know, pushing for this, other database vendors picked up the connectors, picked up the format, and then it has first-class support in tools like Risingwave, Flink, Materialize, all kinds of other systems. They actually do support this change event format coming out of Debezium. And I should put a QR code on it. Good. So let's talk a little bit about Apache Flink then. So, you know, coming back to our mission, we would like to enable full-text search and we would like to get data out of Postgres into OpenSearch. We have solved the first part of the equation, right? We know how to get data as it changes in real time out of Postgres. And by the way, latency could be there like 2-digit milliseconds, something like this, so really snappy. But what we haven't answered yet is, so how do we actually take the data then into OpenSearch? So we need to think a little bit about that part, like the sync side of this data flow. And also, well, very often we wouldn't want to take data as is. We would maybe like denormalize it, adjust date formats, maybe filter some data, maybe have some sensitive data, which we wouldn't like to have in the search index. So we would like to adjust the data a little bit. And this is exactly where Apache Flink comes into the picture. So on a very high level, and by the way, I mean, you have stolen some slides from me, man. So thanks for that. But not that one, but another one. No, and I also stole it from somebody else. But so on a high level, you know, Flink is a stream processing engine. What this means is it does continuous calculations on unbounded or bounded streams which are flowing into the system. So it can take data from a transaction log, like in the CDC use case, but it could also be, you know, clickstream data if you have like an e-commerce application. It could be IoT data, could be logs, all kinds of data which flows into your system in streams in real time continuously. So that's the sort of data. Then there's this compute engine, which is like, you know, it can scale out, it can maintain state and all this kind of good stuff. It does those computations, filtering, aggregations, groupings, whatever, and then you would take the data and put it elsewhere. And so you have those sync connectors there. So it could go then into a data warehouse, it could go into a dashboard, but on the very high level, it's reasoning about real-time data streams. So now this slide looks familiar. Just briefly, what is Flink? Well, we have, you know, a set of different primitives there, I would say. So at the bottom, there's building blocks, which just gives us tools, means for reasoning about events, for reasoning about state, what, you know, getting the event time out of an event. So all those fundamental building blocks. What does it mean to have event time, for instance? Then there's a Java-based API. It could also be, you know, you could use this with Scala, Kotlin, whatever JVM language. But it's a Java-based API which allows it to implement stream processing jobs in an imperative fashion. So that's one way. It's very powerful. You know, this is what you would like to use for very bespoke, very advanced use cases where you might want to interact with a state store specifically, and so on. Going up a little bit in the abstraction hierarchy, you have layered APIs like Apache Flink. We've heard that. So maybe you are building machine learning use cases, AI. We have like Python libraries for that. Well, then Apache Flink would be the natural integration point for doing this. So you could implement those jobs still imperatively, but using Python. There's a table-based API which essentially gives you relational semantics over data streams. So this lets you reason about data streams in terms of tables, columns, and so on, which is to enable the most abstract API, which is called Flink SQL. So there, and this is what I'm going to focus on, there's where we use SQL for implementing those streaming queries. Now, this is a little bit less expressive. So for instance, I mean, you couldn't do like a call to an external web service using SQL. So if this is something you had to do to enrich your data, you would use the data stream API. But if you want to do like, you know, just aggregations, filterings, time-based windowing, then Flink SQL is exactly the right tool. All right, cool. So then let's talk a little bit about how we can use those tools together, Flink and Debezium, for change data capture. Well, in the most simplest case, it would just be a data integration pipeline, right? So you would use Flink And Flink has this notion of connectors, which take data out of an external system, ingest this data into Flink. So that would be a source connector, and there's a Flink CDC source connector based on Debezium. So this would take data in real time out of Postgres, put it into Flink, and then you would have something like a JDBC connector for taking this data and putting it into another data store. So very basic end-to-end connectivity, not too exciting. But then, well, you can add more and more logic to that, right? So maybe, as I mentioned, you want to mask data, you want to remove PII, you want to adjust date formats, maybe you want to, encrypt your data. So all this notion of filtering and mapping your data. So this is something which you could do. This all still would be stateless. As is routing. So maybe you would have some sort of content-based routing. I mean, maybe you have like purchase orders which flow into your system, and you would like to, send B2B orders to that database and B2C orders to that database. So this is something which you could also implement with very simple routing component. It's not just about databases on this other end. It also could be any kinds of other supported systems, and I just put a few logos here, so you get the idea it's a very rich ecosystem of connectors, with support for Elasticsearch, OpenSearch, Apache Flink, Neo4j, Snowflake, and so on. So a very wide range of supported systems there. So now, until now, this almost stateless, but also, actually it's interesting to think about stateful computation. So where we need to, manage some state, maintain state, and reason about multiple event streams at once. And join would be an interesting use case. So maybe you have, I don't know, a stream of purchase orders coming into the system from Kafka. So that's one stream of events. And then you have some sort of reference data, I don't know, country codes, currency codes in a relational database, which you would like to ingest via CDC. So you could do this, you could ingest those two streams, join this data, and then write it out to all those other systems. And then, of course, there's things like window queries and so on. But this gives you a high level intuition. Now I should mention how we can actually use those tools together. And here, what I showed here is Flink CDC, and Flink CDC is essentially it's a native connector built by Define America folks, the original creators of Apache Flink, which takes Debezium and embeds it natively into the Flink process and runs this CDC engine there. And this is, by the way, what can be seen in the middle. It's based on this what we call the Debezium embedded engine. So in this mode, you use Debezium as a library embedded into your JVM-based application. And this is typically what integrators of Debezium would use. So I guess you do this as well at Risingwave, right? So embedded engine. And it gives you all the flexibility you want. On the other end, what most of the people actually do is, if they don't have those bespoke, very specific needs, they use Kafka Connect. So this is also where Debezium originated from. So it's essentially a set of Kafka Connect source connectors. So Kafka Connect being the framework, runtime environment for connectors to be used with Kafka. And this is, I would say, what 90% of people do. So they use Kafka Connect, maybe self-managed, maybe on NSK or any other kind of managed offering. And this is then how they would use Debezium. Then over time we realized, well, people like to use Debezium, they like the capabilities of log-based CDC, but maybe they are not bought into Kafka. Maybe they use something like Apache Pulsar, AWS Kinesis, Google Cloud PubSub, so any other kind of real-time data streaming platform. And this is then finally where the Debezium server comes into the picture. So this essentially has the same role in the overall architecture like Connect, but it gives you connectivity with anything but Kafka. And now with Flink, you of course also could use it with Kafka, right? So you could have Kafka Connect, send in change events to Kafka, then you could use the Flink Kafka source to take the change events into Flink, or you could use this built-in Flink CDC connector. And now, well, when would you do what? I mean, it depends a little bit, right? So if you don't want to spin up Kafka, maybe you really just ingesting change events into Flink is the only thing you want to do, then the embedded engine is fine. But maybe actually you have multiple consumers of this data. You would like to replay those event streams from Kafka and send them into different systems, or maybe hook up new consumers later on. Maybe then you would like to go through Kafka and benefit from the optionality there. Also, I should say in Flink CDC right now, they are quite back behind on an old Debezium version, so if you want to use the latest and greatest Debezium, then Kafka Connect would be the way to go. Cool. So let me just take a look how we're doing time-wise. Okay, it's pretty good actually. So then let me actually go a little bit and show a few things in the demo. So, and this essentially comes back to the original use case which I described, or which I mentioned. So I have some data in my operational Postgres. It's about e-commerce. So I have two tables there, purchase orders and order lines. I would like to ingest them. I would like to join them. I will explain later on why. And then I would like to take this data and actually join it again with shipment data. And I undersold my talk because it's not only about getting data out of Postgres, it's also about getting data out of MySQL. Go figure. So join the shipment data coming from MySQL and put everything, the joined result, into OpenSearch. So that's what I want to show you. And I gotta put away the mic now because I cannot do it otherwise. All right, can you still hear me? I hope yes. Good. So let's get into it. And I have, I run this via Docker Compose. So let me just quickly spin up the stuff which is there. And I have there, my Flink cluster there. I have my databases there. I have OpenSearch there, everything. And by the way, it's also on GitHub in the Decodable examples repo. You can find, this entire demo. So this is what's happening. Okay, so let's take a look then at my data. And first of all, I just can take a look into my Postgres database. So I'm going to use PGCLI for that. And here I have, just some purchase orders there. So you see what's going on. Inventory, purchase orders. And it's just a few rows there. And the data isn't very meaningful, but it's just there for example. So I have that, I have also order lines, and I have my shipments in MySQL. So let me now actually get a client session in Flink SQL, which is how I submit Flink SQL queries and evaluate them. And now in order to ingest my data, what I need to do is I need to create a representation of this data in Postgres. And for that, I'm going to create a table, and now this isn't like your old school regular database table, but instead it is a table which is based on this Postgres CDC connector, which means now this actually runs this change data capture process, and whenever change happens in this Postgres database, the results in this table will reflect, or the rows in this table I should say, they will reflect the state in the database. My schema represents my schema in my database with the columns there, and then all the credentials, connection details, and so on. So let me create this one. And now I can take a look at the contents of this table. So I can do the same thing. I can say split star from purchase orders, and I see what's going on there. And now this is continuously updated. So let me do an insert in my Postgres database. There you go. And now if I don't even need to refresh it, automatically this last line was added to me, right? And it would be the same for updates, it would be the same for deletes. So this table here in Flink SQL gives me a continuously updated representation of my source data. Okay, so that's a good first step. Now I can take it to the next step and join my data with my shipment data, which comes from MySQL. And I already have created this table for MySQL just to speed up things a little bit, so this already exists, which means I now can join my purchase order table, which is the one I just created, with this shipments table, which I already created before. And now I see those join results there. And again, if I add yet another purchase order, then also it shows up here, right? So this also is a continuously updated materialized view. Okay, good. That works also. Now, how do we get our data into OpenSearch? And for that, well, you might have guessed it, I need to create another table, and now this table doesn't act as a source of data, but it acts as a sink of data. So my connector now is this OpenSearch sync connector. It's configured with the nodes in my OpenSearch cluster, like my index, and then the schema here of this table, it represents the structure of this join, right, between orders and shipments, which I just showed you. So let me create this one. So now just having this table, this doesn't really propagate any data yet. So the next thing I need to do is I need to actually establish this connection, and this happens by means of just creating this insert statement. So let me do this. And now you see it says, okay, I have submitted this as a SQL job to the Flink cluster. So this insert now is deployed into the Flink cluster, and it will run continuously. And whenever any change event happens, either on the shipment side, in MySQL, or on the order side, in Postgres, it will propagate this change into OpenSearch. So by the way, you can take a look here at the Flink web UI, and here I see this join. It has graphic representation of those two sources, the join, and then the sync. And then here I could now go about analyzing it and optimizing it, keeping metrics under control, all this kind of cool stuff. Okay. And now also data should be in OpenSearch. So for that, let me actually take a look, and I'm just using the REST API, and I just take a look at one of the documents from this index, and you see, this data is there. Just so you believe me, actually, it's something is happening. So let me insert another one. Let me see what's the latest one. It's 07. And if we get the state from the search index, it's also there. And I haven't inserted the shipment, which is why it's left joined. Just shows my order count. And now I could go to the OpenSearch dashboard builder, create all kinds of fancy dashboards. I could do actually full text search. I mean, this data isn't really meant for full text search, but you get the idea, right? I have this continuously propagated data stream coming out of my operational systems and being fed into OpenSearch. Now, there's one other thing I would like to touch on, and this is, well, so far this was just a one-to-one join, right? And for the sake of the example, each purchase order has exactly one shipment. And this meant I just could join those two tables easily together. But now, for order lines, well, that's a one-to-n kind of join, right? One purchase order can have multiple order lines. So I have those two tables, foreign key relationship, as you would model it. The thing is, now, I really don't want to express this as the sort of rectangular join in the relational model. Rather, in a document store like OpenSearch, I would like to create a nested structure. So I can have the data from one purchase order and all its order lines and everything which else may belong to it in a single document. Because, this is just how I design things there. So then I can do full text search on all those attributes, and it would return a proper, complete document to me. Maybe there could even be multiple tables to them. But for the sake of the example, just those two. Now the question is, how do we do this? I need to somehow take this one-to-n join and express this nesting. And the thing is, in Flink SQL right now, there is no function, or there's no way for me to do this. Instead, what I can do is I can implement a user-defined function, a custom function, which I implement with a bit of Java code, which essentially gets invoked whenever a result arrives on this end side of this join. And I can take this data and essentially just put it into some array, and my user-defined function would emit this array. Then I can register this UDF, user-defined function, as the system, give it a name, like array aggregation in this case, and now I can use it in Flink SQL, and I can access the data in a fully type-safe way. So as you see, it's actually a row representation of this query, which means all this data down to the deepest elements in this structure is like fully typed. It's not stringly based. And I can take this row data, aggregate it into an array, and then emit this kind of structure as we see here. So just to give you a quick example of how this UDF would look like, it's, you implement some sort of interface or class in Flink, and essentially you just need to keep track of this aggregation state. So essentially, whenever an element on this end side for one purchase order comes in, you add it into some sort of array, and if a delete happens, like you delete an order line, this retract function would be invoked. So this means you need to remove this line from this aggregation state. Then there's another function which emits it at the right point in time. So not too complex, but a few lines of bespoke code, and then you can use this in case. All right, so let me actually also show this to you quickly. So for that, I want to create another source table with my order lines. So again, this one exists in Postgres. It has my structure of my order lines table. Now I already registered this, but this is how I would do this. I would, just point to the fully qualified class name. I've done this already. Now I create yet another table on the sync side because now, this schema which I emit to OpenSearch looks just a bit different, right? I have this array structure here. So that's why I just go and create a new table. And could also alter my existing one. For the sake of the example, I'm just going to create a new one. It sends the data to another index, and it has this array structure with my order lines data there. Okay, so I have this. And now I want to go to my Flink web UI, and I want to cancel this existing job. Okay, so this isn't running anymore, and then I issue another insert. And now you see how I go about this one. So here, essentially, I join my tables. So I do this left join with order lines. I still do the left join with shipments because I also want to propagate them. And then, essentially, I group by all the columns of the purchase order side. And then for all the elements which are grouped into the same purchase order, I call this array aggregation function to produce this array of nested data. Okay, so now this is running, and we can take just another look there. So I have now those two joins, right? It's not looking good. Let's see what's happening. Let's see what's going on. For now, let me just take a look at this index. Here we go. Oh, doesn't Flink, of course, rather here. Okay, I think it was just nothing too important. But now I see this is my lines data there, right? And let me just quickly go and, I don't know, update one of the order lines. So let's take that one. Let's say update inventory order lines quantity. So let's say 30. All right. This is good. Update.
You can see ID.
Oh yeah. Thanks so much. There you go. And now, if I get this data from OpenSearch again, my quantity has been updated. And I could add lines, remove lines, but again, the general principle is the same. All this structure in OpenSearch gets continuously recomputed. All right, cool. So then let me go back to my slides. Right, and I realize I'm quite brief on this one, and as it happens, I created a video. There's another QR code which takes you to this video on our YouTube channel, so you can learn more about creating this kind of UDF in Flink. And there's quite a few other videos on the channel which you can check out to learn about Flink. Oh, I love it. That's good. QR code for Flink. Great. Let's give folks another 5 minutes to take a picture of the QR code. All right, cool. And I'm almost done by the way. But now the good thing is I have this upper part of my pipeline, and now I could actually do more things with it. For instance, I could say maybe I would like to have another kind of job which identifies whenever the shipment address has been updated, because then I want to have like a manual process which double checks it's not a fraud, like updating the address. We might find this suspicious, so we want to take this data and send it into some Kafka topic, feed it to some UI, this kind of stuff. And I can implement multiple use cases like it. Once I have set up those connectors, it allows me essentially to ingest this data once and then use it in multiple ways. Okay, so let's wrap up things a little bit. As we have seen, Debezium as a log-based tool for change data capture, it's a very powerful tool which lets you react to data changes in real time, right? I think no question asked. Now with Debezium and Flink, well, I can take this data and process it. I can just build like simple end-to-end data pipelines, just take data from A to B, but I also can clean my data, what I mentioned, removing sensitive data, all this kind of stuff. I could denormalize my data, as we've seen. And I didn't touch on like aggregations and groupings. Maybe I want to feed data into a dashboard. My purchase order revenue per product category, so I could continuously recompute this sort of data and then feed it into some dashboard, all this kind of stuff. And I could do pattern matching, like, I don't know, if I have a stream of credit card transactions Maybe I could look for patterns like it's used in Berlin, like in this minute, and then 2 minutes later it's used in San Francisco. Probably something is wrong with this card. Maybe somebody stole it or somebody hacked our system. So we'd like to flag this kind of transaction, and would like to look for those kinds of patterns in our data streams. Something also which I could do, which is super interesting. There's an entire thing which I didn't mention. So I mean, yes, putting this together, it's quite easy. As you saw, I mean, obviously I spent some time at home to prepare the demo, but it doesn't take too long to build this together. But what do you want to consider if you would like to put this into production? So you need to think about, how do I provision infrastructure? How do I auto scale this? Maybe if more load comes in, I would like to scale this out, and then if my Christmas business is over, I would like to scale it back. How do I do this? How do I go about observability? So I would like to know if there's like back pressure in the pipeline and results are just not flowing fast enough. How do you deal with all this state? Do you want to keep it on S3? What do you do if you need to reload it, repartition it? Long story short, I mean, CI/CD and this kind of stuff, right? Security, you would like to make sure not everybody in your organization can access all the streaming jobs. So long story short, there's lots of operational concerns which you need to consider if you would like to put it into production. And this is why 1 minute or 1 second commercial plug. There may be service providers which help you with this to run this as a software system. All right, and I would like to leave you with this observation, which is unfortunately not my smart idea. I got it from a book from Mark Needham about real-time analytics with about PHP, and he made a very interesting point there. And this is, well, your data as it gets created and gets processed, it has the individual data items. They have very high value initially as they are created, like those credit card transactions. You want to do this fraud detection, you must be very fast. You don't want to detect this potential fraud like next week. You would like to detect it now. So the value of those events, of those individual events, is very high right now, and then over time it diminishes. On the other hand, if you think about aggregated events, the value there it increases over time. So if you look at all your transactions, all your purchase orders of the last year, then you can find very interesting patterns there, right? So maybe you see, okay, those people who are matching certain criteria, they're very likely to order this kind of stuff. If we nudge them and send them some sort of ad. I mean, ad example is horrible, but you get the kind of stuff. You can gain insights into your aggregated data, so the value of aggregations go up. And those tools which we have seen, Debezium, Apache Flink, real-time stream processing at large, they are the building blocks which help you on either side. So reasoning about individual events with low latency, but then also giving you insight on aggregated events in the larger scheme of things. Finally, a few resources. All those projects are on Twitter. Can't believe another QR code sends you to this examples repo. There, you can find this example there and quite a few other things. And I think that's all I have. I would be, very happy to answer any questions.